Greetings everyone, this is Jeff Wilkerson, Professor of Physics at Luther College. This time we got a video that's really aimed for the students in the Introduction to Physics and Engineering Science class, thinking about some of the ideas we were getting to with vectors at the end of class today. So here's a couple of practice ideas. And so this really looks at a problem that was coming up, the next slide in the PowerPoint, that we're going to work on at the beginning of class next time, but there's some ideas that might be helpful as you think about how we were closing class on Tuesday as we head into Wednesday. So that's really what this is. This is about a block resting on an inclined plane. So we have a block here that's resting. So this plane, there's the surface of the Earth, or a table that's parallel to the surface of the Earth, or something like that. And we have this wedge that's shaped like this, and there's a block sitting there, not moving. So this gets us started. We're going to pick up statics. We're going to pick up a class of problems where we're thinking about objects that aren't moving, they're stationary, so that all of the forces and all of the torques on them are canceling out. They're all up in opposite directions and equal in magnitude, so that these things don't move. And so that's what we have going on right here. And so the first thing we were going to think about is how we set up a coordinate system. And it is advantageous in a problem like this to set up the coordinate system. Our inclination, much of your life, you probably wanted to have y be up this way and x be across this way, and that would work. That would be fine. I just want to show you here, we can set up y perpendicular to the surface of the plane and x parallel to the plane, and this is a very convenient coordinate system for us to use. Now, it's not the only coordinate system for us to use. This would work just fine as well, but this one is great. One of the reasons this one is great is to say the motion, if this thing does start to move at some point, the motion would be in one dimension all along x. And we have a force that's along x. Our friction force that's holding this in place is pointed back in the negative x direction here, along this way. The normal force, we said the normal force is perpendicular to the surface, and having drawn y perpendicular to the surface, our normal force now is entirely in the y direction along there. All right? So that seems good. And now the other force that's at play here, we identify all of the forces, and we can say that the gravitational force is straight downward, always straight downward toward the surface of the Earth. Now that's going to have a component that is in the positive x direction, and a component that's in the negative y direction. So that's F gravitational sub y, and that's right there is F gravitational sub x. Okay, so the x component. Now we see, we're not going to work this problem here right now. I just wanted to show you a couple of quick things to get you thinking about how you could set up a coordinate system, how you could identify the forces here. But you see, you have one force in negative x, one force in positive x, one force in negative y, one force in positive y, and boom, we've got these things have to cancel each other out for this not to be accelerating, and in fact, particularly to be static. It's not even just not accelerating, it's not moving at all in this case. So anyway, that's what we got. That's a great way to set this thing up. So we can identify the direction of the frictional force along the surface, identify the normal force perpendicular to the surface, and the gravitational force, and we have the gravitational force in the x direction and the gravitational force in the y direction, and all of this works pretty well. So one of the ideas I want you to think about here, though, is let's move over here. In fact, we probably should draw all of the forces out here. That would be a free body diagram, as we'll talk about next time, as your book talks about. But there's the normal force, and there's the gravitational force. This really isn't to scale, but anyway, that looks like this. And we could calculate let's, just because we want to, not because it's helpful for us to solve anything, but we're practicing ideas related to vectors, right? And we've drawn this over here, and so again, this is the y direction, and this is the x direction. And we could look at this and we could say, let's just, for the heck of it, let's calculate the gravitational force curled into the cross product, the gravitational force cross product with the normal force, the vector product. this direction. So let's do F gravitational cross F normal. And to do that, the way we draw this is we would say, oh, we need that angle right there. We need to take the sine, the magnitude of that force is going to be we're not going to call that theta. Let's call that some other. Let's call that phi, because that angle right there is already theta in our diagram, right? So we have to identify what is that angle right there. And that would give us the magnitude of this cross product. And so as long as we know the normal force and the gravitational force, and we'll work on what those are more next time, but to be able to figure out, what actually is this in terms of the mass of the object, and sort of the frictional force of this. But if we just say there's a gravitational force and there's a normal force and there's a frictional force, and these are the variables of the problem, and theta right there, we can write this in terms of what's going on. And so we can look at this and we can say, okay, what is phi related to theta? Well, we could go through. I'm going to walk you through a way to think about this. We could go through and we could say, yeah, this is going to be easy enough for us to figure out, because what is this angle relative to the surface, and then we got the 90 degrees on up to there, and so we can go ahead and figure all of that out. But I want to just ask you a question: as theta gets to be smaller and smaller and smaller, what happens to phi? As you start to fold this down, what direction is phi going? As theta goes to 0, it certainly looks like phi is going to 180. As theta goes to 90, it looks like phi is going to 90. Okay? So what does that make it look like this must be? Is this 90 plus theta? Is that what that turns out to be? I don't think so, right? Because as theta goes to 0, phi goes to 180. Oh, so maybe this is 180 degrees minus theta. That seems like that might work. Basically, for that to work, what we would have to do is to say, okay, that's this angle right here is what we're calculating on here, or we can do it over here where we've been working, and to say, what is that angle right there? Is that angle right there theta? Maybe, right? Maybe. So we've got this idea right here that angle right there, as this drops to 0, that angle goes to 0, and we can look at that. We say, okay, maybe this is the case, and we can look at this and we can say, if we want to do this, I'm trying to make this legible, but if that's theta, and that's a right angle, that's 90 minus theta, right? We're just practicing a little bit of our angles right there. If that's 90 minus theta, that also has to be 90 minus theta. Opposite interior angles are the same across there. If that's 90 minus theta, then that has to be theta right there, and that clicks. And so that is theta right there, and this angle has to be 180 degrees, a straight line, minus theta. Okay? So now we can say the magnitude of our cross product is just going to be the gravitational force times the normal force, and we'll work more with that on what those actually are next time, times the sine of 180 minus 180 minus theta. So F gravitational, F normal, times sine of 180 degrees minus theta. Now, we might be able to write that as a different function, but this video is getting longer than I intended it to be, so we're not gonna worry about that. We can think about what that actually is in terms of some other function. That's a little bit simpler, but this is fine for what we've got right now. But so that's the magnitude of the cross product. What's the direction of the cross product? Well, we have to put our fingers in the first direction of the first force and curl it into the second force through the smaller angle. This is the smaller angle around here. It's the one that's under 180 degrees. And so it's going to be out of the board in this case. But if this is X curled into Y, out of the board is going to be positive Z because we want a right-handed coordinate system. So we take our right hand, we put our fingers in the direction of the gravitational force, we curl into the normal force, and so we say this cross product has a magnitude of this, and it's in the plus Z or K hat direction, out of the board in this case. So see if this makes sense. See if you can walk your way through some of the geometry that we were doing here and some of the cross product. We just wanted to practice doing a cross product along this way. Hopefully it wasn't too confusing. We will pick this up in class next time. I just wanted to add a little bit because we were right at where we were at the end of class. Hope everybody has a great day. Thanks.